Alright, this is video 001, and what we're doing is we're going to go through how to parse data, put it into a loop in R so that we can have it automatically generate plots for us, which is also going to be preparatory steps for running statistics and so on. There's going to be a few things in here that we're going to change out later in the future, but for the moment, good enough. So the first thing we're going to do is we're going to look at a CSV file. If we look at a CSV file in a text editor, the reason it's called CSV is because it's comma separated values. So every entry has a comma in it. So if we look at this in Excel, same thing, we've got header labels. So we got header, 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 all separated by commas, and then all of our entries. The data we're going to be working with is based on some stuff that I just made up. It's mostly exponential curves with some random numbers thrown in it. By design, this is a enormous data set. Well, enormous being a relative term. It's a 10,000 entry data set, meaning that it's completely and totally impractical to do anything by hand with this. So we're going to have R do all of the corrections for us in the places where I intentionally screwed things up. The reason you use CSV is that it's one of the older formats around, and it's almost universal. It's very easy to work with. There are not many compatibility issues going between different systems. So we're going to use that and treat that as a standard. So look at the R code to give you the file 001, which you should be able to get this and the associated data file from my website as normal. We're going to start going through this. First thing is release the syncs, which allows the console to work. In the future, I'm going to show you how to write data to a log file. So this is just part of my stock header. Leaving it in doesn't hurt anything. Next thing we're going to do is clear the workspace because I have a whole bunch of data left over from my previous runs. We always want to clear things because same reason you clear your lab bench when you go to work. You need to have clear variable workspace. As we've discussed before in some of the intro videos, the working directory, just go ahead and automatically have R set that to the location where you're running this file from. Again, this should be a real directory, not like a Dropbox directory or something. R has some weird limitations in terms of file lengths. And if you start getting into weird temporary extracted directories where you didn't really open a zip file, you just kind of are half running from a zip file, or Dropbox or things of that nature, the file lengths typically cause some, the length of the file names and the paths typically cause some heartache. But anyway, just take all these files, unzip them locally, run them locally. Desktop's cool, or a directory on your desktop is cool. Clear the plot window. We've got leftover plots here from the last time I ran this before I started the video. So we're going to clear that stuff out. So let's go ahead and do that. I'm going to set a breakpoint, and I will do my favorite Control-Shift-S. So I cleaned up everything as described. What I'm going to do now is I'm going to get ready to read in the CSV file. The first thing I'm going to do before I read the CSV file, though, is create a list. This is a variable I made up called NAList of all the things that could be invalid entries in a Excel file. Now, the reason to come up with a list like this, where it's basically all the same syntax of NA, N/A, pound N/A in different cases and so on, is that in the event that either you had people helping you, or you were doing things, 2 weeks apart or 2 months apart or whatever, and you decided to use different characters to mean invalid data, we should not need to go back through a data file and manually clean that stuff up. We can just tell R what all the syntax is for invalid data and have it pick it up for us. As you start finding data that's not processing right and code's crashing on you because you start looking at your entries and you start seeing that, oh, there's some weird characters that you don't know that should be NA values, then you just add this up here and life carries on. So what we're going to do is we're going to use the R function read.csv to very creatively read a CSV file and store it in a data frame named DAT. We use DAT because it's short and I like short names. We're going to read the file experiment1.csv, which because we did our set working directory command, will be in the same directory as the 001 parsing file. As is equals true, and strings equal factors. These are both done so that R does less to help us and we have to do some things manually. We're doing this on purpose, and I'll show you why in a minute when we get there. But these are general good practice because it puts you in control instead of putting R in complete control, and it gives you the ability to be more explicit later on. Header equal true. This is for CSV files where, like the one I'm giving you, where you have a column name for each type of data, and you want R to interpret this as the $, species names. If you have header data in your CSV files, set header equal true. If you don't, you'll have to manually add it later. And then for all the things that are going to be na.strings is built in our syntax. na_list is my variable name. So we're going to let that use that to parse out any missing data. In the data file that I'm giving you, I made all of it up. It's exponential curves with some noise thrown in with a random function. So we'll get to see some things where it'll be somewhat interesting, but it is not real data off of anything. It's stuff that I just made up, and then I came up with goofy names for all the treatments because I need mental help. Anyway, so we'll run first line, create our variable na_list, shows up, read in our data file. We get a new variable named dat, 10,000 entries. Again, this is by design so that we can't manipulate this by hand or expect to manipulate it by hand. More header stuff. Because we've got a whole bunch of junk going on, I want to clear my console. This syntax is going to vary depending on if you're using Windows, Linux, or Mac. But let's go ahead and clear that. You can Google it if you're using Linux or Mac. I'm running a Windows. The next thing we're going to do is there's a couple commands that, because we're running in my favorite Control-Shift-S, if I run these lines, nothing shows up. So I'm just going to paste them into the console and run them manually. Because this is stuff that I'm doing as training, or part of the fact this is a training video as opposed to real code. If I wanted this to show up, I'd have to use the cat statements. But I basically just don't care right now. What I want to do is I want to show you the header data for dat. Head is an built-in R function. And what it's showing me is that I brought in data. I've got my column names of species, treatment, location, sample, date, so on. And that my data more or less looks normally good. Like if I look at date, all these things look like dates. They don't look like heights. I don't have anything massively screwed up here. And that's the whole purpose of stopping to check here. The next thing we're going to do is that we talked about the as is equals true and strings as factors equals false up top. The reason we did that is that we want to have complete and total explicit control of how R is interpreting these things. Because if we look over here at dat when we brought it in, what it did is it picked up the data in different types. So like CHR, that's short for character array, which means that these are just a bunch of letters that R really doesn't know what to do with. What we're going to do with our species and anything that would be considered a categorical variable when you're doing your statistics, like when you talk about doing ANOVAs and Fishers and t-tests and so on, you talk about continuous versus categorical variables. Anything that would be considered a categorical variable in a statistics scope in R needs to be considered a factor. What a factor is that a factor is a special variable type in R where there are only so many possible values that a factor can be. So like for our species of trees that I tested, I think I did like oaks and elms and something else. I did a couple of them. Right now there's no way to ask, or it's kind of difficult to ask R, what are the unique values within species. And then even if once we do get that, there's a lot of weird manipulation required to be able to use that. So instead of leaving it as a character array, we're going to convert it to a factor. That's what we're doing here on this line. Is if we parse this out and read it from inside out, I'm using the function in R called asFactor. I'm going to read the values in the entire column of dat $species. So look at my data frame, anything that's in the species column. And that is going to be converted to a factor and then stored into the variable dat $species, which means it's going to overwrite itself. I'm not going to make a new variable just to store this because, well, I didn't really need the old one anyway. I just need it converted. So I'm overwriting the original. So we look at, it starts out as a character array. I run. It's been converted to a factor with 4 levels. The levels it's telling me are ash, elm, oak, and some other one that got pushed off the screen. I forget what the heck it is. But that conversion's done. We're good. Now, how do we know that we're good? Again, this is one of those functions where I put in something that's a training tool as opposed to a real world thing. I want to see what levels did it get for us. It's telling me that the 4 species we have are ash, elm, oak, and the 4th one I forgot is pine. Okay, assuming that that's what's in our data, cool. Hopefully you know your data set better than this stuff that I made up, because I honestly forgot what I put in there. But in your experiments, you should know what's in there. Let's do the same thing for the treatments. Take treatment, it's currently a character array, convert it to a factor, which if we look over here, it did. Paste this in. What levels do I have? I've got 9 different levels, different treatments I applied to the trees, well, different treatments that I made up, such as I'm going to be doing growth rates on these things, so how does the blood of small children affect the growth of a tree? How does CWC, being my acronym for cyborgs with chainsaws, compared to regular cyborgs, compared to fertilizer, compared to ninjas with chainsaws, and wait, ninjas with chainsaws again? And more ninjas with chainsaws? What the heck? This was done on purpose. I intentionally typed in the treatment name 4 different ways when I generated the data. The reason being, again, when you're running multiple experiments where you have multiple people helping you, or just the fat fingering of life, if we check on things like this, we can see that, hey, we just flat out screwed up and the data's messed up. I have a 10,000 entry file. We're not fixing this by hand. I'm going to show you how to fix it in code. Now, what's also worth noting is that 3 of these are all the same, but they've got different capitalization. So like this one is almost all lowercase, this one's got a bunch of uppercase mixed in, this one's camelback. These levels are case sensitive. So if you bring in data, the first thing you do is you check the header, you call the head function, make sure that things more or less look right for the first couple lines. Then you start checking that all of your categorical variables, you run the levels function on them after you've converted them into factors to make sure that things look like what they're supposed to look like. Otherwise, you've got a data problem reading in data, and you have to go sort that out yourself. We know we've got something wrong here. We'll fix that later. Next thing I'm going to do is I'm going to do the same thing for location, convert it to a factor, because apparently I did this experiment in multiple locations. And then sample numbers. I think I did 20 samples of everything, which is how I got to 10,000 entries. Convert that to a factor as well. So these 4 lines are kind of boring. They're all the same, so I'm not going to spend a lot of time dwelling on the fact that I did them again and again and again. What I'm going to do now is I'm going to read in my date. Now the thing is, the dates can be in a lot of different formats. And depending on what data entry tool you're using to do this, are you typing it in by hand? Are you having some kind of automated computerized device writing you a log file? Where is this coming from? All kinds of different formats. The format I've used in my file is year, month as letters, and then date. So again, just like I had the as factor conversion, I'm doing the same thing where I'm doing a as date conversion. The difference when I do the as date function is that I've got comma, and then I've got some other stuff. This other stuff is saying, what is the format of my date? I know that I used year, month as letters, day. So that's what this means, is %y means placeholder for the year, dash placeholder for month as letters. Because if you looked here, I gave you a couple samples. If it was letters as numbers, I'd have to use %m instead of %b. Same thing that I put in up here just as a chunk of notes. If I'd used underscores instead of dashes for my dates, I'd have to change the syntax as well. There's quite a few different possibilities, and it's generally well documented if you Google it. Point being that this is where you specify format. Because what this is going to do is if I run this once, and if I look at that $date, it looks like it converted my Augusts to 08s. And if you didn't think that I needed help for the name that I named the treatments, you should also Google the date that I chose to start things on, because that has special meaning, particularly related to those cyborgs. Anyway, if I do that dollars date, we'll just pull the first entry, gives me a normal number. What it really is internally storing it is if I do as dot numeric, pretend I can type and talk at the same time, it's really stored a value that's about 10,000. And the way R and most other computer programs handle dates is that they have a date that they start counting from, that's date 0, and August 31st, 1997 happens to be 10,104 days after that. So that's what it's really storing internally. Because we did this as date conversion and now it's internally a number, I can do things like subtract one date from another, which is going to be really useful when we start doing things like calculating growth rates and doing things in terms of, well, what was our average growth per day and things of that nature. So we've got them into a good solid date format now, as opposed to those original just character arrays. Now we can work with it, we can do math, and we can manipulate it later. Same reason we did the factors, because now that they're as factors, there's powerful tools available to us. The height, while it happened to come in as a numerical value, that's just coincidental because of the data that I made up. Yours may or may not. By being explicit like this and saying as numeric and converting the height of my trees into a number, it takes away the possibility of quite a few weird things happening. So that really didn't change anything, but it's a good practice. So now there's two ways we can deal with the screwed up levels in treatment. So again, these are intentionally screwed up. Now let's say that this one that I had here with spaces didn't exist, and I only had the entries that just had different capitalization. I can use this library called string R to convert all of my treatments to uppercase. And then that way, they're all going to be the same, because if they're all uppercase, then they all have the same case, therefore they're all the same, I only have one factor. That's cool. Because I have this one with spaces, we're going to have to do something else. But just for the sake of showing you the simple example, we're going to do a string to upper conversion. So I bring in the library string to R. I'm going to run the function string to upper on the column that dollars treatment. Oops. Trying to highlight and I'm dragging code around. And I'm going to store that in a new column named treatment upper. So we'll run that. And now if I look at that, we can see that I have my original treatments, and then I have treatment upper as a new column. It just did a conversion of all of them for me. Cool. This is easy. What I have to do, though, is that if I ask it, what are the levels, meaning what are all the possible factors in treatment upper, it's going to return me nothing. What the heck? I started with a value of, if I started with treatment, hey, I've got levels. It tells me what the possible levels of the factor are, what my categorical values are. Okay, why not? Because they're still in this old character format. Again, I have to do this as factor conversion. And now, if I run levels of that dollars treatment upper on that column, I am down to just two flavors of ninjas with chainsaws, just the ones with the spaces. So if it's just capitalization, we'd be done. What we're going to do next is, let's say that we have data that's screwed up like I do, and we're going to have to manually fix this. I've decided that the stuff on the right here, this ninja with chainsaws in what's called camelback case, where it goes up and down, kind of like the back of a camel. I've decided that's what I want as my final answer. So what I do here is I'm going to say, we got the equal sign here. So I'm going to say something, the stuff on the left, is equal to, I want to set that equal to ninjas with chainsaws in this case. What do I want to set equal to that? What I want to do is I want any of the entries in dat dollars treatment where, and this is redundant, the entry of dat dollars treatment is this flavor of Ninjas with Chainsaws. I want to change those. So what I'm doing is, if we copy and paste this down, if you remember the video when we talked about syntax like this, where I just took away the big chunk of syntax in the middle, where we've got the square brackets, the number in here is an entry ID in the array, like a row ID, for each individual data. So if I pick like dat dollars treatment 15, that'd be the 15th entry in, or that'd be the value from row 15. I don't want to go through row by row. What I want to do is I want to do the entire column at once, and I want any of the data where dat dollars treatment is equal to, note that this is double equals here because I'm doing a check, as opposed to here where I'm doing a assign value. So anywhere where dat dollars treatment is equal to this Ninja with Chainsaws, I want to convert it. That's what this is doing. So I'm taking my three values of basically bad data and just setting those equal to my correct data. So if we run that, we're going to check and see what's left in treatment. Because, hey, shouldn't this have corrected it? Hey, what the heck, I still got 9 levels. Why do I still have all these other ones? I thought I said I just can replace all of them. The reason is that the way R stores these factor types, these category types, is that once it has been told that a value exists for that category, it's going to assume that that value is still valid, and it's basically going to leave a placeholder entry for it. Okay, well, there may not be any there, but that's a possible answer. It'd be like the question of saying, saying that our alphabet has possible values of A through Z. There's 26 possible values. If we had added a Greek letter, like let's say we added the letter mu, so now we had 27 possible letters, and then we took that one out, R would still be holding the place for mu, even though it's not in the English alphabet. That's kind of what's going on here. That's what this drop levels function is. So what I'm going to do is I'm going to take dat dollars treatment, and so that whole column, and I'm going to run this drop levels function on it. And what that does is it says, check to see what levels are in this column. You know, what possible factors are there. Any of them that don't have an entry that matches a level, just get rid of those because those aren't possible answers because they don't exist anymore. That's what this does. And then we're going to write that back to the original data. So basically we're just updating what possible levels are there. I run that one line, and I run my levels of dat dollars treatment again. And instead of getting the 9 possible answers like I did last time when I ran this exact same syntax, because I dropped the levels that don't have any data, I only get 6. Cool. Carry on. The next thing I'm going to do is I'm going to copy off this dat data frame into a data frame named master dat. I'm doing this just as an example. In a couple of samples, we're actually going to stop doing this, but I just want to get the idea through that, hey, we can copy these data frames off completely as a regular thing, and the idea being that we keep one master set, and then we have a working set. So we're going to copy that off. Master dat gets created as a copy of dat. And hey, we can see that over here, 10,000 entries of each. And all the data types with the factors and everything else came over. Life is good. Now what we're going to do is we're going to do a cleanup function, because I've got master dat, I've got dat, and I've got this NA list. We're not going to need this anymore, so we're just going to get rid of that. That's what this remove statement does, RM. clears them up, just like cleaning your lab bench. Take away the stuff that you don't need because all it's going to do is get in your way. All right, now what we're going to do is we're going to make a copy of master.dat and put it into a data frame called current.df. The reason I'm doing this is that we're going to start running through a big for loop to generate all of our plots. This is not exactly a necessary step in terms of code. This is a step in terms of me trying to teach and beat through the concept that there's the master data frame, and then we're going to start subsampling this. Because what we want to do is we want to look at all the columns that are in master.dat. So I'm going to call names of master.dat, and this is going to give me all the column names. I'm going to copy this off into a new R file or text editor or whatever. Just going to copy these out. And so these are all the things that we have available as columns in our data frame. First thing I want to do is, since I'm going to be plotting these things, you can also think of these in terms of your independent and dependent variables if you prefer to think in statistics terms, and your categorical variables. So basically, what we're going to do is, which one of these is going to be my x-axis? I want to make a plot where my date is my x-axis. I want the height, being the output of my experiment, to be my y-axis. Treatment upper, I'm just going to throw out because I'll just say throw out down here. Treatment and sample we're both going to throw out. The reason we're going to throw both these out is treatment upper was just a part of that conversion where I was showing you how to convert data, and it's leftover. Sample number being, I grew 20 trees of each species and location and treatment for replication, so we can run stats on it. For the first example, we're only going to be looking at sample number 1 of each for simplicity, so we're just going to chuck that for the moment. Because what we'll do later on is, instead of looking at one sample, we're going to do averages and put error bars on it and such, and we're not ready to do that yet. Which means that we've got 3 variables left that are inputs. I have a species, or independent variables, depending if you want to call it that. I got a species, a treatment, and a location. Now, when I make a plot, there's basically 4 places I can put data. I got an x-axis, a y-axis, those are already known. I can put a legend on it, and then I can put a title on it. So what I'm going to do is I'm going to decide that my treatment is going to be what I call a legend variable, which is probably not anything coherent that anybody else has ever called this, but whatever. That's the variable that's going to be on my legend. My species and location, the only place I'm going to have left to show those is going to be in my title. So what I want to do now is I'm going to want to go through my big data file, or big data frame, and I'm going to want to say, okay, so I've got a couple species, like levels of master dat dollars species. Oops. So I've got ash, elm, oak, and pine. I'm going to want to look at only the ash trees. And then once I have only the ash trees, I'm going to want to look at ash trees by location, where I'm going to look at only the ash trees in the forest. Then I'm going to do another plot with only the ash trees in the lab, and then another plot with only the ash trees in the swamp. And then another plot, I'm going to move to the elm trees and do plots for each of those 3 locations. Then I'm going to move to the oaks and then do plots for those 3 locations, and so on and so on and so on. If you remember back to the intro examples I did with basics of programming, and I did for loops, that's exactly how we're going to do this. We're going to put a for loop in to go through each one of these species. Then once we get a data frame that only has that species in it, we're going to do only a single location. And then we're going to do only sample number 1. And then we're going to do, once we have only sample number 1, we're going to make a plot, and we're going to do a plot for, we're going to add a line for each treatment, and then stack up the couple of lines on each other, and then make a new plot, go to the next species and location. So let's go ahead and do that. Again, this little bit of planning here will save you a lot of time. I like these names. You've got better names like dependent variables and independent variables, or inputs, outputs, whatever. You name them. I don't care. So what we're going to do is we're going to ignore this syntax for the moment. That's all commented out because I'm going to come back to that later. So I'm taking master.dat and making a copy of that into current.df. Actually, what I'm going to do is, I'm going to show you the template now. So we're going to take this template code, copy and paste it into our dummy file. I'm going to throw out the throwout variables and uncomment this. If you select lines and press Control-I, it will format them and indent them well for you so they're easier to read. So what we're going to do is we need to get our species first. I need to get a new data frame that only has a species in it. That's what this for loop does. It's going to say, I'm going to change this to for current species in the levels of current.df species. Again, this is basically coming from the master data. So I'm going to have this for loop run once for elms, once for oaks, once for pines. This is automatically going to change my species name each time I run this loop. What this does is, because I now have a current species that I'm working with, I've got kind of a fat nested function here. We're going to break this out in a couple pieces. This chunk here, I'm going to copy this out. Current.df, that's our source data. I got square brackets, so that's index entries. Oops. Copy and paste everything correctly. Current.df, so our source data. Only when the source data species is equal to the current species. Again, this is a template because I'm just taking the word column and keep replacing it with the column that I'm trying to parse on. Right now I'm trying to get only species. Next time I'm going to replace column with location. So what this is saying is give me a result of the current big data set where the species is my current one. So give me only the elms, or give me only the ash, or only the whatever. This is nested inside drop levels. Could I have done this as 2 lines? Yeah. But programmers like to do a lot of nested function like this because, okay, well, I've already got the data where I only have the ash tree data in there now. Just drop all the other levels. So the reason to do this is that, let's say you had done treatments A, B, and C on your ash trees, and then on your elms you did B, C, and D, 2 of the same and 1 different. When you would start running these loops through the treatments, you would find out that there would be no elm or ash trees with treatment D because we only did those on the elms, and the code would bomb out on you because it can't find any entries for D. By doing this drop levels, we're basically just cleaning it up and saying, okay, we're only going to use the loop through the levels of the ones that exist for our current data. Once we get that done, we're going to store this in the current species data frame. Now, so this would give us a data frame. Every time we'd run through this, I'd get only the elms, only the ashes, only the oaks, whatever. Now, what I want to do is I want to get each location. So I want to get only the elms in location lab, I think, whatever I named it. I take my template again, copy and paste it in here. Control-I so I can format them and read them. My current column this time I'm working on location instead of species. So I'm going to loop through my current location, replace column with location. My output data frame is now the current location data frame, which is a subset of the current species. I'll show you how to do that in a second. replace column, replace column. This is another nice thing, is because I always start with the same template. Anytime I see the word column, that means that I screwed up and I forgot to copy and paste somewhere, which happens when I'm talking. And I'll go through the code, step through it, and show you how this works when it's live. Now the thing is, I said for current location in levels of current.df dollars location. No, I don't want to do this based off of current dat. That was my big master one. I want to work off of the data frame that has only my current species, because I'm trying to narrow this down. So current species df. And so now I've replaced my template syntax with the relevant stuff. So now I'm going to get, by the time I get to this loop, I'm going to have only the current species and a single location. Let's look at how this runs. Okay, so step into this, next, next. We can see that my current species is ash. I've got my current .df, which is again is a copy of master dat. Step into it. What it did is it made me a variable named current species df, a new data frame, which, having 4 species, 2,500 times 4 is roughly 10,000. I split these up nice and evenly. If I look at current species, I'm going to see that, I scroll through this, I'm going to see I have only ash trees. That's a lot of scrolling. You got better things to do than watch me scroll. So now, I'm going to do current location within that. I got current location as my forest. This is going to then take this current species df and split out all the entries and only give me the ones that were in the forest. So it's going to take it and roughly divide it by 3, because I have 3 locations. 800 times 3 is roughly 2,400, close enough. Again, checking these sizes is just a good way to do a sanity check as you're running the first couple times, because if you're off by large numbers, you can pick them up here pretty quick and know that something went wrong. Usually what happened is one of 2 things. Either you have didn't check all your levels and you have some of the capitalization or spacing mismatched and you have more levels than you should, or when you were doing your copying and pasting in this template, one of the things that can go wrong, like you saw me do, I left in like a current column and like if I hadn't replaced this current dat with current species, and I'd gone back and pulled data from the main source instead of the one that had already been subsetted, I'd get way too many entries. And that's the kind of stuff that, let's face it, I screw that up all the time. It happens. Check your sizes is the easiest way to do this as you're running through the first time. In here is some code that I'm going to show you in future examples. I put it in here, then decided to comment it out, and I'm not going to talk about it now. But the idea being that we would also be able to, in the future, go through the current samples and do this. For this first example, I only want to work with sample 1. I don't want to work with samples 1 through 20. So I'm just going to say, following the same structure, current sample is 1. Split off my data frame. So take my current location data frame, which is already down to 840, split off only the current sample. I now have 42 observations. We look at that. So I've got each treatment, sample 1, they're all ash, they're all forest. This is also getting small enough where I can now reasonably look at them myself. This plot data is a type of variable called a list that I'm going to make, and we'll deal with this a lot more later. The reason that I make this special variable type called list is if I run this and create it, like a data frame, it collapses in my environment. So the only reason I did that as a list is so that I can basically just hide the junk. And this is going to be a lot of little weird things like what's the label that goes on my x-axis? What's the label that goes on my y-axis? You know, the text, getting this ready for publishing. What's going to be some of my title? Honestly, you don't even know if I use that one, but different story. this all gets expanded later. The next thing I need to do is, because I know I'm going to be using a legend on this, I'm going to have multiple lines on a plot. I want to have a different colors for them, because if and I don't want to do this by hand. Now we saw when I call the levels function, levels of this will give me the names of all of them. I got 6 levels, cool. N levels is short for number of levels. Tells me I got 6 of them. Rainbow is an R function, and if I punch in a number, what it does is these are color codes going along the rainbow spectrum of Roy G. Biv from red to violet, and just evenly split up along the rainbow colors. I have a whole separate video planned on colors, but for now this is good enough, because what this will do is at least I'll get a different color for each line. I'm going to save that in plot data, $colors, as a array. Now look, when I created plot data, I created it as a vector type so that I can save a array into that, and it basically takes all this stuff that would normally be chewing up a ton of my screen space and just condensing it all into one thing. Because the reality is we probably don't need to look at most of it. So what I'm going to do now that I've got some colors, I'm going to create an empty plot. The reason I'm going to create an empty plot first before I start adding lines to it is that right now some of the stuff's manual. We'll get into automation later. But what I want to do is, when you're plotting data, you normally want to have a common y-axis max and min. You're going to want to have a common x-axis max and min. Even if the data for a current plot doesn't take up that whole range, the reason you want to have those common limits is that as you're toggling between different plots to just do a review of your data, you want to see that, okay, well, these ones were way up high, these ones were way down low. The variation in this one was pretty small, the variation in this one was pretty large, just doing your quick once-overs. If you have common scaling values, that's very, very easy to see. You don't even need to read the numbers. So we create this empty plot with the plot function, and then we're going to add each treatment, which again is my legend variable. We're going to add those to the plot with this lines function. So plot, null here means that I'm creating a plot with no data. Type equals O means I think I'm putting dots on it or something. There's some very good information on the web that you can Google for that. I'm going to set my X limit. Here, this is a little bit of automation, to the minimum of my master date and the maximum of my master date. What's my first date and what's my last date in the master? Now, this is one of those times where instead of going back to my limits of my current sample that I've parsed out, I don't want that. I want the data from all of them. So what's the biggest I have anywhere? What's the smallest I have anywhere? Because then that way it's going to be the same plotting limits for every graph I generate without changing them. I could have done the same kind of thing here for Y, but I want to punch in 50 by hand because I had a reason when I came up with this. My X label and my Y label, they're going to come from this plot data guy, where I created this list, plot data, X label, Y label equals stuff. The reason that I do this is that I'm going to reuse these in a lot of places, and that way it's fewer places for me to fix. When we get into doing ANOVAs and things of that nature, I get into this much more heavily, where it's very few entries, a lot of copy and paste, and it just runs. So I'm showing them now. This plot data $counter, this is counting how many lines have I added to each graph. The reason I need that is that my colors over here, they are an array from 1 to 6. Well, I need to know which color I'm going to use. So this is just to tell me, keep track of which one I'm on so I can update my color. Easy. So hit next. Makes me a plot. Yay. Nothing on it as predicted. Got a Y limit of basically 0 to 50. If you remember me showing you the dates, how those were big numbers as opposed to actual human readable dates, they're here. There's a whole lot of discussion about that in a different video. So for now, just accept the fact that they're numbers instead of coherent stuff. So now what I'm going to do is I have my current sample. which had 40 some entries in it. Now what I want to do is I want to plot each height versus the date for a single treatment. So here, we went back to my template again where I do my for current column in levels of stuff, dollar column. Same template I pulled out. Whoops. Same template I pulled out over here. I'm doing that again. So I've got 3 of these nested now. What this is going to do is it's going to give me the a data frame for only the current treatment. Step into it. And if we squish enough stuff around, we can see that my current location is forest. My current treatment is the blood of small children. Because apparently that does something to tree growth. And then I'm going to add the line for current treatment height, which is my y-axis. Whoops. With the tilde meaning height relative to date. My color is going to be come out of that colors array, so I got plot data dollar colors. And then I have plot data dollars counter, which is where I keep track of that, which I'd already made a 1. So I'm going to be color number 1. And then that adds a line for it. Beautiful. For loop finishes up at the closed curly brace. Comes back up to the top of the for loop. Now my current treatment is cyborgs with chainsaws. It's going to add a line for cyborgs with chainsaws, which probably doesn't show up very well because it's yellow. Run it again. Now I've got just regular cyborgs, which does not go quite as low as my cyborgs with chainsaws because, you know, you give a cyborg a chainsaw, it can reach lower and destroy more things. Yeah, I need help. Anyway. So now we're adding fertilizer. Fertilizer, cyan line, got to add it in here. Current treatment. Now we have ninjas with chainsaws. Turns out that those guys are like bonsai masters and they just make everything grow. You know, they're not destructive like the cyborgs. And then I think I had water or something in here. But whatever. Anyway, so we've got all of our lines on here. Cool, that's data. We can start looking at this. Now we need to add a legend. The legend syntax is built in R. First thing I have to do is I have to tell it where do I want to put the legend. I need to give it X and Y coordinates. The X coordinate is going to be the minimum of my x-axis, which I can go back to my master data and know that it was the first date. I'm going to pick 50 for my y height because that's what I picked out of a hat for this data sample. I have to tell it what's the text that I'm putting into my legend. I can do that just by asking it what are the different levels in my current sample for treatment. Because that's the same thing that I ran through on this for loop here. I'm asking it the same question that I asked up here. It's going to give them to me in the same order, so it's going to fill in my legend names for me right away. CEX and LTY are plotting and scaling things. We're going to skip those for the moment. Because I stored those colors as an array, it's also going to put in the correct colors for my legend. And then I have a title for the legend of things which kill trees. And, as promised, we get the legend. Cool. Now I need to put a big title on here. That's what the title function does that's built into R. Paste, just like cat, takes a bunch of little short things, separates them with whatever variable we give them. I chose nothing because that's my style. So it's going to spit out species is my current species, then a comma, so we can read it humanly, space location equals current location. So we can see all the stuff I typed in. It read the current species, read the current location, put it on the title, bang, done. The next thing I'm going to do is call this system.sleep function. This is a weird little quirk in R of if we run these things through at full speed, it basically has a graphics problem where it will say doesn't properly allocate memory to save the old plots. So instead of dealing with all the craziness involved with that, what we do is we put in the sys.sleep function. It's basically a call out to Windows, so those of you on Mac may need to adjust this. That says just wait here for 0.1 seconds. In the future, what I'm going to do is, because of all the weirdness and scaling and how these things come out, I'm going to show you how to write them to a file, so your plots are not dependent on where you set your margins, because as we change the margins, things scale differently and so on. It's R, whatever. Like you get weird stuff like I just showed you here, where that's not nicely fitting anymore. So we go through, and we keep looping through this, and as promised, we looped back up to the next current location. We're still on our ash tree. My current treatment is water. Oh, sorry, my next location is my lab. And it's going to loop through, add me a new plot, put data on there, and then say species is ash, location is lab. And we're going to keep stepping through this. And you guys can do this on your own to see that the variable names keep updating. Because part of the reason for seeing this is that it gives you a chance to debug. So go ahead, and I'm just going to run it to finish it. Yeah, here we go. Ran it to finish it. So if I go back through these, I get each species, each location, all the different treatments, so on and so on and so on. So now, while it seems like this took a lot of effort to set up, let's say that, okay, the next time I run this, I want to make my location my legend variable, and I want to put my treatment up here. It's not too hard, because what you're basically going to do is take this entire set of stuff, copy and paste it, change a couple entries up here, where you did your for loop up here. You're going to change a couple entries in this for loop, and you're done. And then when it comes to, I've got a better template even for the ANOVA type data, because ANOVAs are common for the obvious reasons, where it's even fewer things to change because better templates. So hope this is useful to you. Enjoy. Bye.